So what I'd like to talk about now is I'd like to talk about first order linear differential equations and a particular technique called the integrating factor that we'll use in order to solve these first order linear differential equations. So the first thing that I want to do is I want to know when it is that I'm actually looking at a first order linear differential equation and when I can have something that I can in fact use this integrating factor for. So the first thing that I'm going to do is that I am in fact going to divide through this entire function here by x, okay? And that's to get the coefficient in front of y prime to be a 1. So this is going to now be y prime minus 2 over xy equals 2x ln x. Okay, now a couple of things that I want to notice. One is that this function here, p of x, right, which equals negative 2 over x, and this function here, which is called f of x, which equals 2x ln of x, they're both functions of x only. And so hence that makes them linear. That makes this entire differential equation linear, is because all of the functions that are in front of the derivatives of y are all simply functions of x, including this one, which is what we'll call big F of x. And the second part is that this is first order because the highest order of the derivative is 1. We have the highest thing here is the first derivative, and so consequently that makes this a first order linear differential equation. Now that I have this form, what I'm going to also notice is I'm going to notice that I can't actually use separation of variables in order to solve this one. If I move over this function here, okay, if I try to move that one over, then and try and factor out my x's, for example, in order to allow for separation of variables, I can't actually separate out those variables, and so hence things get kind of a little tricky, and so consequently separation of variables doesn't work as a solution method. Instead, what I want to do is I want to get the right-hand side of this equation, this whole part of the equation, into a form that will allow me to then integrate both sides fairly easily, okay? And it turns out that what I'm going to want to do is I'm going to want to multiply by this I of x equals e to the integral of p of x dx. And notice p of x is this function here in front of the y, okay? So if I just remember, if I have it in the right form, right, where I have a 1 in front of the y prime, okay, and what I have in front of the y is a function of x only, then I can actually utilize this integrating factor. So in this case, I have I of x equals e to the integral of negative 2 over x dx, okay, which will then equal e to the negative 2 ln of x, right? And there'll be a plus c here, but we're actually going to end up dealing with that at the end, okay? That's going to end up being dealt with at the end. So consequently, we don't need to deal with that now, okay? And so this is going to then equal e to the ln of x to the negative 2. And I actually want to bring that power in because it kind of makes things a little bit easier to work with, okay? And then this is going to then equal x to the negative 2, okay? Now what I'm going to do is I'm going to take this function, okay, and I'm going to multiply both sides by that function. So I'm going to now have x to the negative 2 y prime minus x to the negative 2 times 2 over x y, okay, equals x to the negative 2 2x ln of x. Okay, and after some simplification, I end up with x to the negative 2 y prime minus 2 over x cubed y equals 2 over x ln of x. And now it turns out that what I have is I have something here that I can easily integrate. What I'm going to notice here is that this thing, that these two, their derivative, the function in front of the y is actually a derivative of the function in front of the y prime, and that the y prime is the derivative of y. All right, and so what I notice here is that in fact what I have is I have the chain rule, but except backwards. Okay, so what I can do here is that the derivative d dx, okay, of x to the negative 2, the integrating factor, times y, that actually ends up equaling if I utilize the chain rule, that's going to end up giving me negative 2 over x cubed times y plus x to the negative 2 times y prime if we utilize implicit differentiation. And so consequently, this is exactly what I want because that's really easy to integrate. Once I integrate it, I'm going to just simply end up with x to the negative 2y. No problems, right? So I'm going to integrate both sides now. I'm going to use my newly constructed right-hand side. I'm going to take the integral of x to the negative 2y. And I'm going to set that equal to the integral of 2 over x ln of x dx. Okay? On the right-hand side, simple. The integral of that guy is just x to the negative 2y, right? Utilize the fundamental theorem of calculus. You just get back what you had to begin with. And then this is going to now equal, we'll use a u substitution, so we're going to let u equal ln of x, and we'll have du equal 2 over x dx, or excuse me, not 2 over x dx, but just 1 over x dx. Okay, so this is then going to give me 2 times the integral of u du, which is equal to 2 times 1/2 u squared plus c. And then when I substitute back in, I just end up with ln x squared plus c. All right, and we know now that that's equal to x to the negative 2y. So that's my c ended up showing back up, the one that I'm going to actually need in order to put into my initial conditions. So it ended up coming back at the end anyways. Okay, so now what I have here, all I need to do now is I just need to now multiply by x squared. Okay, so I'm going to multiply by x squared. And that gives me now y equals x squared ln x squared plus cx squared, where c is some kind of constant. And that's the general solution. This is my general solution. To review, 1, we first want to confirm that we're working with a first order linear differential equation. Okay, that is that the functions in front of each one of our derivatives of y are all functions of x only, and that the highest order derivative is a y prime. It's a first derivative. Then the other thing you want to do is make sure that you can't do separation of variables. Because if you can do separation of variables, you might as well just do that because it's really easy. Why find an integrating factor? Okay, kind of a waste of time. So once we've done that, we confirm, okay, that that's the case. Then what I'm going to do is I'm going to make sure that the coefficient in front of y prime is a 1. Okay, so by, in this case, we divided through by x, all right? And then that gives us our function p of x, which is the function in front of y, all right? So our integrating factor now is going to be I of x equals e to the integral of p of x dx. We go in, we integrate, and then we're going to multiply through by both sides. It turns out that what we're going to end up with, okay, is always going to be d dx of I of x y. That's actually how we wanted to set it up to begin with. That's why we utilized e to the integral of p of x, all right? So in the future, you don't actually have to go through this whole step of multiplying through by both sides. You just, you can actually construct your left-hand side, okay, by using d dx of ixy. And then your right-hand side, you are going to have to make sure that you multiply through by the integrating factor, okay? Then, like we always do with differential equations, we're going to integrate both sides. After integration of both sides, we end up with our general solution. And that is how we utilize the integrating factor to solve first-order linear differential equations.